Now you've seen matrix multiplication before, obviously, even if you're a bit rusty on it. So I'm not going to start from scratch. Instead, I'm going to present it from a slightly different point of view that's more useful for our purposes. So really, I'm going to break it down into three things that you need to know. Number one is that you have an inner product between vectors. So if x and y are both column vectors of the same length, remember all of our vectors are column vectors in this course, then x transpose y is a row vector times a column vector, and it's done the same way as what you call the dot product in vector calculus. And we can either write it out or we can use sigma notation, whichever seems more convenient. The second way we can multiply vectors is an outer product. So here we have two vectors that are not necessarily of the same length. And now the ordering changes. So before we had row times column, now we have column times row. And this is just every possible pairwise multiplication of elements from the two vectors that we have as operands. So the inner product is always a scalar. Sometimes it's called a scalar product. And the outer product is a matrix. In this case, the dimensions are given by the lengths of the two vectors in the operation. And then really, all matrix multiplication can be done in terms of those two things if you apply them in a blockwise sense. So this is easier to explain by example than anything else. So here's a 2 by 3 matrix times a 3 by 2. If we use letters to denote the rows of the first matrix and letters to denote the columns of the second matrix, so everything's a vector now, but if you ignore that those are vector entries, it's really a column times a row again. And that's an outer product, which we write this way. And then each of these is an inner product that's well defined. So the answer is 2 by 2. Okay, so in general, you can do m by n times an n by p. Those inner dimensions have to be identical or it's undefined. And then the outer dimensions tell you the size of the result that you get. A couple of important rules. You lose the commutative property. AB does not have to equal BA. They're not even necessarily both defined, but even when they are, they're not necessarily the same. So we have to preserve the ordering very carefully when we do matrix multiplication. On the other hand, we do have our good old associative law, and we actually use that a lot in our manipulations. Finally, I'll remind you the identity matrix is a diagonal matrix with ones on the diagonal, and it serves as a multiplicative identity.